Hello everyone. So today we continue our calculation problem examples from this video. And today we talk about the topic 5, the wind power generation system. Specifically, the problem we're gonna deal with is a three-phase squirrel cage induction generator system operating at certain speed and the voltage. Speed given, voltage given, and also telling you the operating frequency and the power. Other information about generator are also given as number of poles, 8, and per phase, RS, XS, RR, and XR. Okay, ignoring RC and LM, we will try to find the A per phase circuit model, B the electromagnetic power, C air gap power, the last the grid received active and reactive power. So let's start it. So the first thing is try to have the per phase circuit model. So circuit model includes 5 components. Now, so 3 resistance and 2 reactances. So 4 of them are directly given as per phase values. Very nice. Shown here. So 0.2, 0.8J, 0.13, and 0.8J as givens up here. So what I'm missing is one is the phase voltage across these 2 terminals, and the other thing is the resistance here. We need to calculate, which we recall as a speed dependent, or say the sleep dependent value. So first of all, this voltage across these 2 terminals is a grid phase voltage in RMS value. Okay, because later on when we calculate the power, we need RMS value. So we're trying to have the phase voltage RMS value labeled here. Okay, and given 220 volts here, be careful. First of all, it is RMS value, very nice. Second, it's line voltage, not phase voltage. Second thing, we need to calculate this resistance value, which is following this formula. Sorry about the box, is not very neat, but anyways, we need to deal with these 2 things. So first of all, the phase voltage RMS value, because the given is again 220 volts line voltage, so we need to divide by square root 3 to have the per phase voltage in RMS value, following also this polarity, very important. And as to the second resistance value here, we need to do some calculation here. So obviously we need to calculate the sleep. Sleep, according to the formula, is equals to synchronous speed minus the generator speed divided by synchronous speed down in the denominator. So the key here, or say the very tricky thing, is you need to be very careful about the unit. The given generator speed here, 1000, is in RPM value, so be careful your synchronous speed also want to be in RPM, same unit, so that you can do the operation between them. So the formula of synchronous speed is 120 times frequency divided by number of poles, and exactly in RPM. So this synchronous speed minus the given 1000 RPM divided by this synchronous speed in the denominator. So very nice. In other words, be careful. If the given generator speed is in radian per second, and then you need to have synchronous speed here times factor of pi over 30 to convert it to be radian per second as well, so that you can operate with the 1000 radian per second. Anyways, going back to this particular problem, the S turned out to be -1/9. So here, negative sleep is clearly indicating a generating operation. So it makes sense, it is generator. And based on which we calculate this resistance value here. R sub R is given as up here 0.30 and then times the sleep ratio, and so we equals to -1.3. So we got -1.3 as a result of this resistance. So this is the complete answer for question A. Obviously, we check it. So per phase SCIG circuit model, based on which we go ahead to calculate the power we need. So the first thing we need to do is find the generator current, which is following this direction. Okay, and it's leaving the generator because of the generation operation mode. So according to this generator current, we are calculating the generator current, which is equal to the voltage in the numerator divided by the total impedance in the denominator. Here, be careful, we have a negative sign in front of the voltage. That's because of the polarity of the voltage supposed to introduce a current flowing towards right. However, we know the generator's current is towards left, so when we're looking for it, we need to have a negative sign in front of the voltage. So after calculation, we end up with a phasor current with certain amount of magnitude and phase angle. So based on which we go ahead to find the power we need. Here, to find the power, the key is to be clear which component among these five is or are contributing to which power we are looking for. For example, the first power we're looking for in this particular problem is the electromagnetic torque power. We know very well, first of all, this power is contributed by this component and this component only. So we just use a formula 3 times the magnitude of the current square times the impedance of this component. So it equals 3 times 67.88 square times the impedance value, -1.3. Here, be careful, this 76.88 is the magnitude of the current, because here, the magnitude is really minute without phase angle. So it ends up with a -17.97 kilowatts is the active power in watts, and also we have a negative sign here, which indicating delivering power from the generator to the grid, making perfect sense. The next power we're looking for is the air gap power. Again, air gap power is contributed by these two components, which we need to be clear very well at first place. And then the power is just equals 3 times magnitude of the current square times the total impedance between these two components. Turn out to be R sub R over S. And then after the calculation, end up with a -16.173 kilowatts. Negative sign indicating generating again. So the last one is question D, the grid received active and reactive power. So we can feel free to use the three-phase apparent power equation, which is equals to 3 times the phase voltage in RMS value times the phase current in RMS conjugate. So the voltage is equals to 220 over square root of 3. The current RMS is 67.88 with conjugate. So end up with a phasor. Obviously, we want to convert it to a complex number, which telling us both active and reactive power. So by the sign of active and reactive power respectively, we can easily tell the grid is actually consuming the active power, positive, and providing, or say feeding, the reactive power towards the SCIG. So this is actually one of the drawbacks of SCIG wind system, in where we need to compensate the reactive power consumed by the generator itself. Alright, so this is all for this topic. Thank you, and let me know your feedback.